Hello everyone, do you see me? And do you hear me?
Yes to both.
Okay, very nice. Okay, I think I have left open the waiting room so everyone can join. Let's start, and then eventually people will arrive. Let me just share screen here. Okay. What need to do. Okay, so yes. So yesterday we were talking about apart from the overview, the detailed overview that we gave, we were talking about this introduction to statistics, no, or at least a reminder. I hope a reminder of the statistical concepts that we are going to use more or less during the whole set of lectures. And so the topic of today, so we start like a more proper topic on the practice of machine learning, which is in the context of regression. In the context of regression problems, I will discuss the problem of overfitting. Okay, so this is going to be try to cover today most of it. So probably you remember from yesterday what we were showing in the slides. We're showing something like this. So we were showing some points, some data points here, and these data points here could be fitted by many models. They can fit this with a model like this, or I can fit with this with a model like this, or I don't know, with another model. But as you increase the complexity of the model, then you may encounter situations where, for example, you go through all your points here, or very close to all the points, but it doesn't seem to be that this is a good model, and the reason is that it doesn't seem to be, let's say, this. Let's put it like this: model gray, this modeling gray. Is maybe not the generating function of the data we are seeing, okay? Which is what we are after, right? So eventually, what at the fundamental level, not only in statistics but also in physics, or mainly in physics, we are interested in the law of nature. So the law of nature will give us the expected value of some output, right? And the expected value of some output, let's say, it is like defining the generating function of some data, right? So what we are after is, let's say, the expected value of the output. Here the output y is a random variable, and this random variable, every time you do an experiment, you will have different realizations, noisy realizations of some physical law, let's say, no? But the physical law will define or will determine the expected value of given by physical law. Physical law right? And this will determine the PDF, the probability distribution function of the data. Right? This is essentially what we are doing. Also, when we do statistical inference, so also in statistical inference. Right, so this model in gray doesn't seem to be the correct model of from which the data was coming from which the data was generated. No? So then actually this model is doing this sort of overfitting, and overfitting is that it is following that close all these points that were used to fit the line, that if now you have a new point, let's put a new point here in, I don't know, in green. So this new point, which may have an output like this, will be poorly predicted by this model that overfits the data. So in a way, what I'm saying is a good model for the data is a model that doesn't overfit, that doesn't do overfitting. Of course, not underfitting either, no? What I'm saying is that now imagine that you have a model, a very stupid model like this one, okay? So this horizon, this is just a constant, and this model obviously underfits the data. So you don't want this either. So there is an intermediate model complexity if you want here, and this is what it's all about in machine learning. Okay, so last lecture what we saw was how to, so you remember that from this summary in statistics that we were fitting a line with the mean square. So yesterday we saw how to fit a line with mean square error. And the mean square error, we saw that it actually comes from maximum likelihood estimate. It is just, you know, I mean, when you propose the likelihood of your data, you maximize this likelihood, which is the same as minimizing the minus log likelihood, sorry. And the minus log likelihood is directly related to the mean square error. So this is an example of a fitting, let's say. But now what we are going to do is to introduce regression. So by using a family of models that we saw also in the overview, family of models, like the following. So a function of some data here, which can be can have several dimensions, and that's why I put a x as a vector, and also will depend on some set of parameters. It's going to have this shape. Is going to be a combination, a linear combination of some functions here. So what I'm saying here is that these functions, so this is my catalog of nonlinear functions. It doesn't have to be nonlinear, but I mean, if this is a linear function, then it is a trivial thing. So it would be a linear function in the end, but let me put it like this: potentially nonlinear functions. So this type of model, just keep in mind that this is the function that I am using to fit the data. So this is the function just to put it in a statistical context. So this is the function that determines the mean of the PDF of the data. For example, I have a Gaussian here where the likelihood of a given point in my data set will depend on this f, because this defines the mean, if you want, xi, right? With some variance, okay? But just keep always in mind that whatever fitting function you are doing is actually determining the mean of the distribution that you are assuming for the data. So so once you have defined this function, so okay, I want to have a function like this, and I want to fit the parameters W here, which are the parameters, no, the weighting parameters of, or the weights, if you want, of this genetic generalized model. So this F here is called in the literature, particularly in the Bishop book, generalized linear model. Obviously, this is in general not non-linear for the input, which is x, but it is linear in the sense that you have a linear combination of non-linear functions of your input. And this is the reason why, even though so as you will see right now, this the optimum parameters here, they have a closed form solution or an analytic solution, and this is quite convenient because I mean, by proposing, if you want, a catalog of very flexible non-linear functions, and by choosing the number of functions in your catalog to be large, you could potentially fit many arbitrarily complex data sets if you want to know. So what I'm saying is that even though this is a very simple example with an analytic solution, it is very powerful in general. So let's then try to fit. So the idea is now let's fit the parameters W. So I am putting inside this vector or all the WM here corresponding to this model that I defined here. Okay. So then the first thing I will do is just to put this function in a more compact way. I will just rewrite this function as this. Okay. So you see that I have done nothing here. I'm just like putting in a compact way this scalar product defined here. So the vector of phi will contain all the catalog of my nonlinear functions, and the vector of W contain all the corresponding coefficients here. And note that, for example, in a linear model, you have a constant term, right? So this, in general, when you build this sort of model, this will have one has a first component times sorry, as a first component, and second component phi1, phi2, etc. Right? Phi I don't know, phi m or something. Okay. In such a way that, for example, if now I will recover from this the linear model, right? So I just say that my catalog of functions is only one, phi1 is equal x. So, and then I have my I recovered let's say my straight line of yesterday, right? Is there any questions so far? Please just this lecture is not going to be as dense as the one from yesterday, because yesterday I tried to put 2 lectures in one. But it is important for me for you to that you understand as much as possible what I'm saying. So just interrupt me if there is any, and interrupt me by audio, please, because okay, I see things in the chat, but I am usually quite focused on what I'm saying, and I usually don't follow the chat. Anyway, so this is the way in which I will work in order to find my coefficients. Okay. Then, as we saw, so now you assuming the data, so my output is Gaussian, then I can find the maximum likelihood estimates of my parameters by minimizing the mean square error as yesterday. So let us do that. No, so the mean square error here is just this sum across all the data points of data minus my prediction. Let me put it like this. Square. Okay. So what I'm doing here is to okay, I will just write the form of this function, which I have just written above. Transpose times, yeah. Okay. I have been disconnected from one. I don't know why. Is it? Do you still hear me?
Yes.
Yeah. Yeah.
Okay.
No problem.
Thanks. Okay. Okay. So what I will do now is to minimize this with respect to the W's. Okay. So if I do this, then I will just differentiate. So by differentiating, I have this times phi. Let me put phi I, which is phi evaluated in xi, just to be quicker here, times the transpose of phi I. Okay. You can convince yourself that this is the case, because I mean, if you do this component by component of W, you need you realize that you need to multiply at the end by the transpose of phi, and not just phi, let's say. Okay, so if I do this, at this point, what is convenient is to introduce. So let's introduce a matrix here, which is capital Phi. I think in some literature this is called the feature matrix, and this will be the following. So this will be a matrix such that the first column is just ones, has many ones as. So this is a matrix which is, by the way, the dimension of phi is n times n plus 1, where m is the for example, in the case of a polynomial, is the order of the polynomial, right? So then here I have phi 1, phi 1 x 2, etc. Phi 1 x n. Okay. Then the same here, I have phi 2, because I have many functions in my catalog, phi1, etc., up to, I don't know, phi m of x1, phi m of xn, right? So this is my Fisher matrix here, my phi matrix. And then this function, this matrix is going to be useful in order to put it in a convenient notation, this expression here. So I want to make this be equal to 0 because I am just finding the minimum. So let me do this. So this expression is going to be equal to. So okay, I forget about the -2, but let me just put like this. T minus the sum of the second term, I transpose, and this is equal to 0. And then and this is the moment where you can express this, for example, the first and the second term using this matrix I just introduced above, which is capital phi transpose times the vector of output, the vector of observations, if you want, right? So you see it, no? For every point, I am so every point here means every column in my phi matrix, in my phi matrix. Okay, so I can express this first term like this one, and the second term analogously. It's straightforward to see that this is just the multiplication of capital phi transpose times phi times w, and this is equal to 0. Okay, from which I have at the end, let me put it in another color, the maximum likelihood estimate of my weights, of my parameters or coefficients, whatever you want to call it, is this inverse times transpose times y. Okay, so in that sense, so this is one of the few models in machine learning where you have an analytic solution for the optimal for the parameters of your model, for the coefficients, for example, of this catalog of functions. And actually from here you can extract. So this is generalization of the solution that we saw yesterday. That was like the first assignment, right? So solution for linear model using the same cost function, which is the mean square error. Okay, so this is an important result that we will use. At least today, we will use a lot. So let's actually, I think this is a good moment to show some code that actually implements this. So what we are going to see now is a data set that I'm creating, and with this data set, with this data, I will fit this sort of generalized linear model to this data that I am creating in a synthetic way, let's say. So let me stop sharing here and share screen in my computer. Share. Right. Do you see my screen? Oops.
Yes.
Okay, great. Okay, so what I'm doing here is is the following. So this is a Python notebook. I am assuming you are familiarized with Python notebooks. And then I will share this Python notebook with you today. But let's just try first, at least, to understand in general what the code is doing. And if you have later any question, you just tell me why this line or why this other line. But this will be like later, right? So when I share the document with you, the notebook with you, and if you don't understand something, you write me. But for a moment, please just try to understand the general logic here. And then what I'm doing here is to generate 12 data points. Okay, well, probably, how can I increase this size? Is it better like this one? It's probably, if it is too small, just tell me, okay? Because I don't know.
It's pretty good.
Okay, so what I'm doing here is to generate 12 data points from this sinus function with the x going from 0 to 1. Just I do this by just adding Gaussian noise. So let's say that if my function is just this one, 2 pi sinus of 2 pi x, then I'm just first of all creating one data point, one output for each input here that I am creating. Let's say 12. I'm creating 12 points. For each of them, I am evaluating this function, and then I am adding noise to this function such that I mean this noise is following a Gaussian distribution where sigma is 0.3, let's say, and mean equal to 0. So if I do this, I obtain this sort of plot, and this is just the generating function, this sinus of 2 pi x, and I just plotted here the points where with the error bars, which is just the noise that I am adding. Okay, so what we were doing is to use a polynomial model to fit the data, and the polynomial model here by following the same notation as before. So here I am using this generalized linear model, where my catalog of functions here are just expansion. I mean, powers of x, right? So it's 1 because I always need the constant term. Then x squared, etc. So this would be if you want a polynomial of order m here, in such a way that the prediction is just this function here. For a vector of one-dimensional, here I'm talking about one dimension only, just to simplify the problem. I'm talking about, so this is an array, a one-dimensional array of some n points. And then I have some weights here. Then my prediction is just, for each term, I am just adding x to the h power, where h goes from 1 to the order of the polynomial, let's say. Okay. So this is a way so this is a function. The spread here is just coding what this function is upstairs. Okay, so if I do this, I know that the coefficients, these w's, these parameters, I know that I just saw that the optimum parameters, they have an analytic form given by this. So the maximum likelihood estimate of the parameters is just this. I just wrote this in the notes a few minutes ago. So which is just the matrix phi, phi transpose minus 1, phi transpose times the vector of all the observations. When I put in bold here, it's just a vector, right? So let's fit in a degree 3 polynomial. It's done like this. So I just say that my polynomial has degree 3. And I am building my capital phi. You see this feature matrix that I introduced before. So this feature matrix is the following. I first start with a column of ones, and this is the way in NumPy of doing that. I just start with a column of ones, and then I will stack. I will stack horizontally. Let's say I will just increase in number of columns, as many columns as the order of my polynomial. So again, from I have this loop that covering the order of a polynomial. I am stacking columns corresponding to x to the h power, let's say. So in these simple terms, I can build this phi, and then I can just build this maximum likelihood estimate, which is the inverse of phi transpose times phi. So I have an inverse here with this common times the transpose. So I have this dot, right? Transpose of phi times the vector of y. The vector of y is a vector of all the observations here, right? So this vector that I am building. Okay. And then, for example, let me print this for a given value of the polynomial. And if I do this, I get the following thing. First of all, there are 3 coefficients because this is order 3 polynomial. Sorry, 4 coefficients because one coefficient is for the constant term. So I have 4 coefficients for an order 3 polynomial, and the coefficients are this one, okay, and the line, the fitting line is just this one, the red one here. Okay. Now, imagine I do the same for degree 5 and for degree 8. I repeat exactly the same procedure here. And for each of them, I build my maximum likelihood estimates here, and then I am plotting. And when I plot this, I get the following. So I get that I had an order 3 was the red line, right? So order 5 is the blue curve. And I went to order 8, which is the green curve. So you see here that already order 8 is doing some sort of overfitting, right? And let's look what happens with an even more extreme polynomial, so order 9 polynomial, where I am now printing, if you want, printing the values of my coefficients here. So an order 9 polynomial fitted to 12 points is going to look bad like this one, very badly. So this is a strong overfitting here. And just compare these coefficients here that I have obtained by fitting an order 9 polynomial to 12 points. Compare this, you see order 10 to the 6, 10 to the 5. You see at least 100, which is but you see, I mean, the order here is that this is the coefficient for the constant term, for the linear term, for the quadratic term, etc. So you see that the coefficients, they even increase in general with the power of x. So compare this order of magnitude with respect to the order of magnitude that we got by fitting an order 3 polynomial, which is sort of reasonable, right? Okay, so what is the origin of that? So why I am obtaining such large values of the parameter for the coefficients is because of the following. So the maximum likelihood estimate, the maximum likelihood solution for this model is this one, is this equation here. And what is actually happening is that the matrix phi times phi transpose, which is called the design matrix in some literature, this is becoming singular. Okay, so And if of course, is as you overfit, this matrix is more and more singular, then of course the inverse is going to explode, and then that's the reason why the explosion of these coefficients. So why this matrix is singular is another story. So let me put a simpler example here. So in this example, this is just another notebook, but this is just I was playing with that, if you want. So imagine you have 2 data points. I have 2 data points here given by these 2 values. Okay, I am fitting a degree 2 a quadratic polynomial. So it's just I am fitting a parabola with 2 points. Okay, so then the corresponding phi matrix is this one. It's a 2 by 3 matrix. And when I get the determinant of the phi transpose phi, which is the design matrix, you see that the determinant is very, very small. So as you increase the number of columns with respect to the number of rows, and in particular when you see here that the number of columns is larger than the number of rows, this will give you in general a 0 determinant design matrix, and consequently a singular matrix which is making exploding the maximum likelihood estimate. But I mean, this is an algebraic result that is just a result of the following. I'm trying to fit a parabola to 2 points. Obviously, this is not enough, right? I need 3 points to fit a parabola, no? But all this logic behind translates into this effect of having a large number of large coefficients for sorry, I went too far. Large coefficients for a model which is highly parameterized with respect to the data points you have at hand. Okay, and this actually is making fine-tuning, because all of these very large coefficients, that they can conspire such that you actually pass through all the points. Okay, so is there any questions so far? If not, I will share the other. Okay.
Will these codes be available for
Yes.
us to, check? Okay.
Yes, you will. There is actually homework on this code, but
okay.
Not yet. Yeah, but this
Okay.
is going to be available.
Sure, thank you.
Yes, I have a question too.
Okay.
With this method, you do not know the error, right, of the parameters? Or you can know?
The error of, sorry, the error on the W's.
Yeah.
No, I mean, I am following a frequentist approach, which by construction, at least a priori, doesn't provide errors with the coefficients. Another story is that then you do bootstrapping with this solution.
Okay, thank you.
Okay, but just like this, yeah, I'm just providing a best fit. What I was trying to say. Okay, I'm trying to share this. You remember the bootstrap that we talked yesterday, right? So I don't know who posed the question, but
yes.
That would be the way to address uncertainties.
Okay, thank you.
Okay, so so let's go back to this. So the thing is that so before going to how can we solve this issue, how can we address this issue, just note that this model complexity here given by the order of the polynomial. So the model complexity here, the optimum model complexity should be intermediate, because if it is too simple, we'll underfit. If it is too complex, it will overfit. And actually, this is analogous to say that you will have a bias variance trade-off. It is the same as that because of the following. So imagine I am so let me how to put this. Okay, so imagine I am saying, okay, my true output of X, if my true output is some function here that I am trying to estimate, plus some error, some noise here. So if this is the true underlying an unknown function, if this is the case, then I am trying to so what we do, in other words, in machine learning, is we estimate this by some, let's put it, some function, some estimate or some f hat here, which depends on some parameters, okay? And what I'm saying is that if the function is too simple, then the variance of this estimator, which can be, I mean, I'm pretty sure that you know how to compute the variance, is just this one. So this will be low or small, sorry. This will be small for very simple models. And the bias instead is going to be large. So the bias is, remember, the bias was just defined as the expected value of your estimator minus the true function here, right? And just here, remember. So remember that when I'm putting this expected values here, this is with respect to different data sets. Different data sets or experiments. So this bias instead will be large for very simple models. So you remember if I am taking, if my
Sorry, Brian, but we can't
hear you
talking
anymore.
Yeah.
Brian, I think you're muted.
Yeah, I don't know. I just disconnected again. So something's happening today. But do you hear me now?
Now, yes.
Yes. No problem now.
The thing is, I need to be aware of like two screens at the same time because then I don't have other way to have a feedback of whether everything is going well or not. Okay, so but you got this, right? So you got the fact that these expectation values with respect to different data sets. Did you hear this or not?
No, I don't think so.
Okay, so what I was saying is that for very simple models, the variance is very small. Like for example, for a constant model, the variance is very small because it's very stable. Or for a linear model, it's also very stable. It is not wiggling like this. However, the bias is very large because you are far away in general for all data points. And this is by defining variance and bias in this, like this, which is the definition, and where the expectation value that appears in this definition is with respect to different data sets that you may encounter. So you do one experiment, another experiment, and then you do expectation with respect to the experiments like this. Okay. So then the idea here is that if now the mean square error is, you can actually, mean square error is actually a consequence of computing the expected value of this quantity, where this x is a new point unseen before, let's say, test point, call it as you wish. So then you can demonstrate that so you can demonstrate that this is equal to bias square times, plus the variance plus the inherent noise of data, which is something that you cannot reduce, right? So there is an irreducible source of noise, which is coming by the noise of the data itself. I don't know if there any. I will try to mute all the. Yeah, sorry, I mute everyone, including myself. Okay, so do you see this? Is it?
Yes, we can see your notebook.
Okay, so actually so let's put another homework here, another assignment. So try to get this result by, from this you try to compute using this definition. You try to compute the fact that the mean square error is a linear combination between bias and variance plus the irreducible noise. So in this way, this good model is a trade-off. This is what I'm saying. It's a trade-off between bias and variance, because of a simple model, this will be low, but this will be very large. And a very complex model has a polynomial for the 9 in 12 points. You will have very small bias because the model will go through all the points very closely. But since this is a very wiggly function, the variance is going to be very large. And there's something in between here, that there's a complexity, an intermediate complexity, which is actually can be thought of as a bias variance trade-off. Okay, so how to avoid overfitting?
Sorry, Brian, I have a question. So actually, yes, this formula in red would give us an estimate for the error on the parameters using a frequentistic approach?
No. This is the error you are making. This is you see the expected value across different experiments or data sets of the error you're making with your approximation.
Okay, thanks.
Yeah, so this is not related to the error associated to the parameters of the model I just fitted. Which is associated to the error I'm making by not describing well enough the data. Okay, so how to avoid overfitting? Okay, so this question, okay, you may have different strategies. The first strategy, which is a trivial strategy, is to try to increase the number of points, the number of data points. So try to increase the size of your data set. And this is intuitive, right? So in order to, if I try to fit a polynomial of order two to two data sets, right? So this would be badly overfitting. But if I now have 5 data points, obviously a parabola can very well fit my 5 points. So by increasing the size of the data set with respect to the number of parameters I have, this will help in general to increase the number of points. So an heuristic criterion is to have more or less between 5 and 10 times the number of parameters of your model. This is actually coming from a very formal development related to this thing that I actually quoted yesterday in the overview. This pack bounds from probably approximately from computational learning theory. But okay, I mean, nowadays, as I was also saying yesterday, this is not very used in practice. Also because, I mean, you have the data that you have, so it's not something that you can play with. Sometimes getting data is very expensive, right? So this is a solution which in practice is not very convenient. Okay, so then the other solution that I'm spending more time here is the typical solution in machine learning, which is the training and test splitting of the data. Okay, this training and test splitting. And this is one of the most popular ways to handle overfitting. It's not the only one, as we will see, but one of the most popular ones. Okay, so here the idea is the following. It's just the idea is that we want to have a decent prediction of our model. So the motivation to have a good prediction of our model for new data points. So imagine that, I mean, this in eventually what you want to do in machine learning, but also in physics, probably is to predict what would be the point, the result for a given new point, right? That you arrive, so you build your model, you do your experiment, and then you try to say, okay, with the model I have fitted to this data I just received, I will be able to predict what is going to appear. And so in order to do that, so in other words, or if you want, in the jargon of machine learning, this is a model that have nice, if nice is the correct word, but generalization properties. Nice generalization capabilities. Capability. Okay. In the sense that it's a model that generalizes as good as possible. Okay. So here, as you may know, so you have your data. So if your data is, I don't know, a number of points here, then you just do some of the points. Let's say you just take these points and you do your training or your fitting. And with these points, you do your test. Okay, so this is in a way the data for training, the training, and this is the data for test, the test. So the procedure is simple. So for each model of your catalog, so make the fit or the train. You make the training here to the training data, which is to say, I will have a maximum likelihood estimate. Let me put this now with a hat to be my estimate for the parameters of my model age, which will be Rmax, the likelihood, and the likelihood is evaluated in the train data, if you want, given these parameters, right? Because I am a model age, and you do this. So you do this for all your models. Okay. And then, as a second step, to evaluate the performance of these models in the test sample or in the test data set. And choose the model giving the best result in terms of highest likelihood. So what I'm saying here is that the best, I don't know how to, I think yesterday in my slides, I wrote it like this. The best model, let me put it like this. This will be the Rmax across all the models of the likelihood of the test data, where I evaluate this likelihood in the fitted models that I obtained before. Okay. So what one expects is that as the model complexity increases, so let me put here model complexity in general, because this applies to genetic, not only polynomials, genetic models. So the error, let's say, or if you wanted the -2, or forget about the 2, the minus log likelihood. I'm talking about the test data set. No, sorry, I am putting a generic plot here. Is the following. So you expect that you obtain this for your training, for your train data set, training data, while you are obtaining this for your test data. So in other words, if you have a too complex model, the effort you're making on your test data is going to increase. No, this is what you expect to happen, right? And here, of course, this is a region. So this is a region of where there is underfitting here. So this is a region of high bias and low variance. So underfitting. And this is a region. This is a region here of the contrary. So low bias, high variance, overfitting. So complexity here should be chosen to be somewhere here. Okay, the optimum complexity. No. So more or less around here, you have optimal complexity. All right. And let's make a pause. So let's before going to for 5-minute break, I will just show you a small code, and then we continue later after the pause. Let me share screen. Yes. Okay. Do you see my notebook?
Yes, yes.
Okay, good. So what I'm doing here is to do this training and test procedure. So what I'm doing here is to say, okay, I have some data points. I have, I think, 12 data points I started with, and then I am splitting my data points in train and test for the input and for the output. Okay, by doing like this. So I am, if you want, shuffling, because that was shuffled from before randomly the points, so I can just from this randomized points, I can just take the first 40%, let's say, of the points, assign this to the test for input and output, and the rest of the points I will assign them to the train. And for each of them, I am plotting here I am plotting the following. So, and the thing I'm doing here is to plot polynomials from 1 to 10. So from order 1 polynomial to order 10 polynomial. Okay. And then I'm doing exactly the same as I did before. So I am building my phi matrix like this. This is not new. This is what we saw above. For each of the phi, of course, phi will depend on the order of the polynomial here, right? But I am making a loop over the order of the polynomial if you want. For each of them, I create, or I compute analytically the maximum likelihood estimate, and I compute the training error and the test error. Training error is just the mean square error, in this case, where I compute the mean of y train minus the prediction evaluated in next train. And I need to evaluate the prediction in this input with these coefficients that are just fitted, let's say. And then I do the same for the test, where I compute the mean from the test data points, the test outputs, with the prediction on the test, which is the prediction evaluated on the test input with the same coefficients, optimum coefficients. And then I plot. And when I plot, I got this. This is the order of the polynomial in the x-axis, and the error I'm making, the mean square error I'm making on the y-axis. And here you see that the red line is, this corresponds to the training error, and the blue line corresponds to the test error. So you see that the behavior is more or less as expected. So there is so at the beginning it is high, so then it goes down, and then it goes up. And from this, you could conclude that the best model is something between order 3 and order 4 polynomial, let's say. Order 4 is here. Actually a little bit better for the splitting I just did. Is there any questions on that?
Brian, I would like to ask, is there any general rule on how the blue curve changes with the number of test data?
With the number of test data. Yes, I will talk about this in a few minutes. Yes.
Okay, thanks.
If not, if I would reflect to this question. If it is not clear, just please ask me again.
Okay, thanks.
Okay. Okay, so if this is clear, let me go back to my notes. Okay, so probably let's do the following because it is already close to 8 past. So I will make a break here, and we can resume in 5 minutes if you don't mind. So 5, which is 13 past, and I continue with the lecture if you agree. Okay.
Yeah. It's okay.
Okay, good. So let's resume at 14 past because it's already 12:09. 14 past. See you now. Okay, so let's continue. Am I online? Mm-hmm. Do you hear me?
Yes, but maybe people is still on break. I don't know.
Yeah, okay. They will enter at some point. Thanks. So okay, so let me share screen here. No, this one. Okay, so what I am what I just did was to fit this polynomial, and then what I was doing is to select, if you want, the optimum order for the polynomial, the optimum number for the polynomial with respect to the test data set, if you want. This was the one that allowed me to evaluate the point beyond which, the point in model complexity beyond which I am doing overfitting. But probably, so, but note that this depends on the splitting I'm doing here, right? So if I do another splitting, or if I select other points, in general, this result will change a bit, right? So for example, let's, if the points now are, we have another seed here. I put just a random seed for reproducibility, but let's try to do another seed here. So instead of this seed, I put I don't know, 1. Okay, sorry. Okay, I have other points here. And then or other data set. Imagine that I perform a second experiment, because all of this is referring to different data sets that you may have, right? So if I do this, and then I go to, and I do the same here. So what happened now? I need to, okay, I probably need to evaluate the whole book. How do I do this? Run. Okay. Let me go through all the steps again, because I needed to some definitions that I was not evaluating. Spread probably was the thing that checking. No. Phi stack. I didn't cover phi. Sorry, I thought that I was computing this at some point. Nothing. So nothing works. Let me just start again. Sorry. Phi x phi. Okay. Now we are getting somewhere. Okay, this is badly overfitting because this is a 9 or the 9 polynomial. Let me see if now I can. Okay. So you see that by changing the data set, I obtained something a little bit different. Of course, the trend is the same, but now it seems to be that is order 2 instead of order 3 or 4, and then it goes to do overfitting, right? So this is, in general, this is not something that we desire. So we desire to, what we would like to, is to have something in general that generalizes when to whatever data set we have. Okay, so and then in order to address this, then what we do is a procedure that I'm showing now. Yes. Sharing screen. So the procedure to find the best model in general. I mean, what I'm saying is with respect to different future data sets. So the procedure is called k-fold cross-validation. So k-fold cross-validation is a very simple idea, but it's quite powerful. So the idea is the following. So first of all, what you do is to randomly split the data set in k subsets, of course, of identical size. And here, let me just put it diagrammatically like this. So I have all my data sets. I split my data sets in k batches or something. Okay. And then you do for the kth part, it's a small k part. So you fit the model with the remaining k-1 parts, and these k-1 parts are going to be your training, and evaluate performance on this part that you have chosen, on this kth part. For example, you may start saying that in the first fold, you select this, and then you reserve this for test, and then you fit the models with all the rest. In the second fold, you reserve this for test, and then you choose this and the rest for the training, etc. So in the third one, you reserve this and you fit the rest, etc. So this is something that you repeat if you want. Repeat for k equal 1, 2, up to k. And you average. You average all the test errors. Okay. So let's say the test error that you're committing that you're making in a given model is going to be the average of all the test errors given by all these k-fold procedures or iterations that you did. Okay. So this is something that mimics, if you want, the fact of having different experiments that you may be able to make, or different data sets that you may have the chance to get, right? And this is what, in general, the best model is going to be the one that generalizes the best across different data sets, not only one, of course. Okay, so which value of k to use? Which value of k to use? So let's see some examples. Imagine that I have as many folds as number of data points. So if I have this, I have the following advantage is using as much training as possible. Because if k is equal n, then the test sample is only 1 point, you see? So you are dividing your n data sets in n batches, but then every batch contains only 1 point. Each batch contains only 1 point. So in this way, the advantage is that, okay, you are using as much training as possible while reserving only 1 point for test, right? So the training here is n-1, right? So here it may be good because the bias may be small, right? Because you're using as much information as possible. So the disadvantage here is that the variance is high. Disadvantage. The variance across datasets is high. And it's also computationally costly. And it is computationally costly because you actually need, you need n trainings. And if a training is costly because your model is very, very complex, then this may be even more costly. I mean, n times as costly, right? Typical values are k equal 5 or k equal 10. Okay, this is more or less the preferred values in the community. Then something I forgot to say is once you have, let me put it like this. Once you have selected the model that has the best or the smallest average test error, what you need to do at the end of the day is to fit all the data, to fit the selected model, to all the data. Okay. Anyway, what I'm saying is that what happens if I choose 5 or 10? So suppose we have, and this is now the part where I think I may address the question that was posed just before the break. So imagine that I plot as a function of the number of training as a function of the size of my data set. I plot 1 minus the error. Okay, so what would look like this curve would look like something like this, right? So in general, in the sense that by increasing the number of data points, I am making sure that the error is not in the test error here is smaller. So I'm approaching to 1 if you want. Then assume, for example, that I have, in this small example, assume a data set with 200 points. So imagine that I have 200 here. I'm just, let me put this more. So this here is 1 minus error, the error. So imagine that 200 gives you, I don't know, 0.82. Imagine that 100 gives you 0.8. And imagine that, I don't know, 40 here gives you 0.6. So imagine I have this situation, just it's a hypothetical situation. If n equal 200 and I choose 5 folds, I mean k equal 5, then the size of the training set is going to be 160 points. the size of the test is going to be the remaining 40 points. Then actually K5 here, so this is going to give you a good estimation, right? This is going to give you a good estimation of the performance. Because actually, if you believe this curve I wrote here, I draw here below 100, sorry, above 100, then the error is not changing too much. So then already with a training point, a number of training points which is equal to 100, then I would actually obtain a pretty decent idea of the true performance of the model, right? So, however, imagine now that I only have 50 points in total. If I have 50 points in total, assuming k equal 5, the train is going to be 40, the test is going to be 10. And then here, k equal 5 will underestimate the performance, because I would be here, right? I would be here. I would say that okay, I may estimate that the performance is of 60%, when in reality it's a performance closer to 80%. So the message here that I want to make, the moral of the story here, is that k equal 5 or 10, they work normally good, normally well enough, normally well for sizable data sets. Okay, whereas for smaller data sets, the option of k equal n is probably better. With all the disadvantages that they have, of course. Okay. So this is more or less how one could think about the behavior of k, or sorry, the behavior. I mean the behavior of this k-fold cross-validation procedure as a function of the number of parameters. And then, so before that, before saying what I wanted to say next, I would like you to take the previous example that I put, where in this notebook I obtained for a specific choice of training and test. I obtained some curve on the test error and some curve on the training error. And when I changed, you saw when I changed the data set, I obtained something different, right? So what I would like you to do, so another thing that you may do is to implement k equal 5 cross-validation on the sinusoidal data set that I showed before, which is you make sure that you are repeating the same procedure by choosing batches of your data different batches of your data in this consecutive way that we were showing up here. Okay. I will give you all the tools for that, and the notebook, etc. So it is just a way to implement this k-fold cross validation, which in general is just 4 lines of code. Okay. Right. So far I have a model. For example, we have fitted a model with which is just the polynomial model. So I only need to fit here the coefficients of the polynomial. And this is a simple model in the sense that, for example, in the sense that it doesn't contain hyperparameters. So the existence of hyperparameters complicates a bit the procedure, because imagine the hyperparameter is the following. For example, you have a hyperparameter. You have a neural network. In a neural network, you may have all the parameters that you have given an architecture of the network, right? Given the number of layers, etc. So, for example, in a neural network, a hyperparameter can be the number of units or neurons in a hidden layer, or the number of hidden layers in general, or you name it, right? So there are many things that you can change in a neural network. And then this procedure of k-fold cross validation, the simplified procedure, is not enough, because you may want to obtain, so you want to select the optimal value of the hyperparameters as well. Hyperparameters, right? So in order to do so, what you need to do is to complicate a bit this scheme of k-fold cross validation, and to do instead the following. So you do some, let's say, train here. For each model that you train, you evaluate the performance in a validation batch of your data set, and then you choose finally the model that performs the best with the test data, right? So if it were not for hyperparameters, you don't need this third, you wouldn't need this third subset of your data set. But the fact that you have hyperparameters means that here you select the model with optimum hyperparameters. Okay. So you need this third level of splitting of your data, and this one here is, as before, you fit all the models with all the hyperparameters if you want, no? Here, and then you select the best model here, but this best model here may select for you a model for a fixed number, for a fixed value of hyperparameters, but then you need to have a third data set, sub data, sorry, in order to fix your hyperparameters. Okay. All right, so this is probably all I wanted to say about cross validation and training and test splitting. And I will go now to, I will finish this lecture of today with another overfitting control method. Is there any questions so far? Okay. Do you hear me at least? Because probably I'm always afraid that.
Yes, we can hear you.
Yes, we can hear you.
Okay, very nice. Thanks. Okay, so let's finish the lecture with another way to control overfitting. Which is the regularization methods. Okay, so the idea here comes from the observation that this model we overfitted, like for example, this polynomial for the 9, so we'll have very large coefficients that we saw, right? And we saw the reason behind this behavior is that this design matrix is becoming more and more singular. So what we are trying to do here is so the idea here is to somehow penalize large values of the coefficients of the parameters in general when doing the training or the fit. I'm doing the fit because I don't want you to mix up with the training and test, etc. So when doing the fit, I would like to change a bit my procedure in order to avoid somehow these large values to explode because I am having few number of data points and a lot of features, a lot of independent variables. Okay. So a very popular alternative is to fit the model. So this is very popular. Oof. Alternative is to fit the model using this cost function, 1/2. So this first term is the same. Let's say, oh, let me put here an I. Same as before, right? But here I am adding a term having this form. Okay. This is actually called the rich cost function, or in general, the rich regularization method, if you want. So how does the optimal value of the parameter change it with respect to the one where this term didn't appear? So you can one can see the following. So let me call this error rich or something. So if I differentiate with respect to my parameter, then what I end up having is the following. So I end up having this term was similar to the one I got before, and this other term was also present. Actually, the solution is just this one, the previous solution, let's say. But then I am getting an extra term here, which is because I have this extra term in the cost function, I have an extra term here in my derivative here, So when I solve for W here, what I have is the solution, the rich solution for the optimal parameters is the design matrix as before, plus some alpha, this constant alpha that it is yet to be like optimized, times the rest. So the only change here was in this term here, where this matrix is a unity matrix a little bit modified. So it's a unity matrix where the first column is 0, 1, etc., 0, 0, 1. So it's like a unit matrix. But with the first column being 0. And this corresponds to the fact that what I am doing here is to, in the design matrix, what I am trying to modify is not the first column of the design matrix, but all the rest of columns. Okay. So this, but you can, I mean, this is easy to check from here to here, right? Okay, so then this is doing all the job. Sorry, there's a -1 here that I forgot. Okay, this is doing all the job because this matrix was singular. But if I add here this term, I am regularizing this matrix. So at some point, by this innocent, apparently innocent addition here, I'm actually regularizing the singular behavior of the object I have here, and thus I am avoiding eventually the explosion of these values of the optimal parameters. Okay. So let's see an example of that. Let me see what I get here. Okay. So let me change the screen. Okay. So the bridge procedure is the following. Imagine I am doing this exercise of fitting a polynomial of order 9 with the same data set I had before. Let me go to the previous data set. So let me put here again 2, 3, 1. Okay. Just to, yeah. Okay. So what I'm doing here is to start with the same data set I had before, and instead of, okay, I build here my phi, etc. Has before. This is as before, just an order 9 polynomial. And now I am adding to my optimum solution this regularization here. So this is I am inverting, instead of phi transpose phi, I am inverting phi transpose phi times this regularization. And this regularization is this term that I just mentioned here. With that given alpha, I don't know, 10 to the minus 10, or e to the minus 10, let's say. So my regularization term is this constant times an identity matrix where the first column is 0. And when I do this, then what is happening? Let me see if this goes okay. So look at the values of the coefficients I got, even for a polynomial of order 9. The optimum values of the coefficients here are quite reasonable, right? So they are not 10 to the 6 or something. They are 14. They are 9. I mean, this is reasonable sizes. And this comes from the fact that this determinant here that was 0 or very close to 0, if I don't put regularization, this is a determinant which is 10 to the minus 48, and that's why the matrix is singular. When I add the regularization, it is still small, but much less smaller than previously. And when I do this, what I obtain is a value. So let me see, because something changed. Let me put here instead, which was the previous solution. So what you see here is that by fitting a polynomial further 9 to the 12 data points using the rich regression, you obtain the blue curve, as compared to a polynomial further 9 without regularization, which was the previous case and represented here by the red curve. So you see here that with this small value of this constant alpha that acts as regularizer, I just obtained a very nice fit of my highly parameterized polynomial, even though I have few data points. Okay, so this shows the possibilities that I was also commenting yesterday, of the fact that nowadays there are very popular models which are highly parameterized, like convolutional deep networks with I don't know, probably millions of parameters. And even though they are highly parameterized, because they work in such a way as the fit is obtained with regularization methods, they usually are able to fit the data correctly and not doing overfitting, even to simple data sets, which a priori wouldn't require such a complex model. Okay, so this is more or less what I got for the rich regression or regularization method. So is there any questions so far? Because now the lecture is over, more or less. No questions?
Hello?
Yes.
Can you hear me?
Yeah.
Yeah, I wanted to ask, with the regularization method, do we have now any way to estimate an uncertainty on the parameters?
Still no.
I ask this because I read somewhere that this regularization procedure was connected to maximizing the posterior probability with the kind of a Gaussian prior on the weight, right?
Yeah. So what you're doing is probably something method which is called dropout in neural networks, which is sort of a regularization, but as we will see in the next lecture, so I don't know if tomorrow, the day after tomorrow, on Thursday, we will see that this regularization here is can be interpreted as coming from a prior. So when you do, when you write, when you are now in the framework of Bayesian inference, now you write the likelihood of your function, and the likelihood of your function may give you a cost function whose minimum is found at this value without the regularization. Now, what you are doing in Bayesian inference, as we were commenting yesterday, is to, instead of maximizing the likelihood, you maximize the posterior. So posterior is just likelihood times prior with some normalization that you don't care right now for this task. And then the log of the posterior, the log of the posterior has this log of likelihood plus log of prior. And when you compute the log of a Gaussian prior, you obtain exactly rich regularization. If the prior is standard, if the Gaussian is a standard Gaussian, okay?
Claro, no, però vull dir, per què fixeix alfa? Saps el que te vull dir? Com tries aquest valor?
So what we are actually what we will see tomorrow is exactly this Bayesian interpretation, where which provide by with the need of having a prior, it is actually providing a regularization, because the log of a prior is actually something. Imagine that the prior is Gaussian. The log of a prior is quadratic in the parameters. So, which is exactly the shape I am showing here for Rich.
Okay. So if you interpret this in a Bayesian inference method, then you can have an estimate of the uncertainty.
Yeah, this is the whole point of Bayesian framework, is to have uncertainties. But so far, I am using. I mean, what I can say is that Bayesian works very well, because one, it provides uncertainty. This is your ultimate goal. But two, also by construction, it implements overfitting control. How does it implement overfitting control? Because the prior actually enters as a regularization term in this treatment here. Okay, but by itself, this is a regularization method. I am not interpreting anything so far. I am not trying to build here a posterior distribution of my parameters. I am trying to obtain optimum parameters using a modified cost function, right? That allowed me to avoid overfitting.
Okay, thanks.
Okay. Everything is connected in this sense, in the sense that there is a connection. There is a prior. There is a specific prior in the Bayesian inference that gives you rich regularization. And we will see that in the next lecture.
Brian, so in the example that you have shown, it seems like the 0 degree constant, like, and the eighth, they are very close to 0. So maybe those parameters are actually not needed, no?
Which parameter, sorry?
The one that goes like x equal to 0 and x
this one
equal to 8. Yes, so they are very close to 0 compared with the other.
Okay.
No? So maybe those parameters are not very relevant.
Okay, I agree with you that they're less relevant, but I don't know if now you I don't know. I mean, I haven't done the exercise of how would that look like with these parameters being 0.
Yes, but the rich method actually doesn't, if you can reduce the number of parameters, I mean, it does not tell you like what is the right number of parameters that you have to use, right?
No. Rich regression is not about choosing a model. Rich procedure is about avoiding overfitting for a given model.
Mm-hmm.
Yeah. So you see here, if I compare this with the polynomial of order 3 without regularization, I don't know if I had it. Yeah, here, the red line.
Mm-hmm.
It's more or less similar, right?
Yes.
So if it is more or less similar, it will give you similar test errors. And it would be hard for you to differentiate, to do this sort of curve here. So because if you do rich for all the polynomials, then you will have like a flat curve for the test. something like that. So that's why, I mean, I think of it in a separate, as two separate methods to avoid overfitting.
Because I mean, somehow overfitting is also connected with reducing the number of parameters, no? So
yeah, so if you are doing overfitting, means that your model is too complex, so you need to simplify your model by reducing the number of parameters. Yes. Yeah. But what I'm trying to give you as a message is that the reach you can have. I mean, I haven't tried. I am improvising here, but imagine that I want to fit a polynomial of order 15. I don't know what is going out, but probably alpha is yeah. So you see what happened previously. We had nice behavior. Here it's still nice. I mean, it's still not wiggly, but you still but now you have a little bit more. They follow a bit more the training the training points. So if what I'm trying to say is that if you will now go to a polynomial of order 20, let me see. Yeah, no, it's still good. At some point, if you increase a lot the order of the polynomial, you will need to increase your alpha, right? But you see that because of thanks to this regularization, you will get for a very high number of parameters, you will get a reasonable fit. Okay. This is something that you can try. Actually, you could try to play with this by playing with alpha. So now that you say it, let's make it an assignment. So try to play with alpha here. Okay. And try to see if alpha is close to 0, try to see that you are getting an overfitting of a polynomial of order 9, for example.
okay.
Okay.
Thank you.
Yeah. Any other question?
Yes, I have a question. Can you hear me?
Mm-hmm.
First, is there any physical or natural interpretation of this reach term that we put on the error function, on the cost function, or is it just something that we find that it does the job and we put it? And yeah, also, if alpha is yet another hyperparameter that we need to play with, depending on the along with other things like the architecture. Yeah.
Exactly. So the first question you pose is related to the first to the question that I had before, Raquel. It's related to the fact that you can interpret the reach term as coming from a prior on your parameters W. So I have a physical motivation to imagine that I have a physical motivation to think that my parameters are Gaussian. So I have a Gaussian prior.
Okay.
And then if I have a Gaussian prior, when I could compute the log of my posterior, it will produce this rich term. This we will see tomorrow on that.
Okay.
Okay. And yes, again, for the second question, the alpha, the value of alpha is a hyperparameter that you would need to optimize. So alpha is related to the variance of your prior at some point. And this is a value that you could optimize and you should optimize. But depends on what you want to do. If what you want to do is just to fit a line, then you say, okay, for some alpha which is good enough, the fit is reasonable, and I'm good to go. But in general, yes, you should optimize your alpha.
Okay, thank you.
Okay. Good. Other questions? Okay. If not, we can close the session, and we can resume probably on Thursday, I think, at 11. Okay.
Okay. Thanks for the
Okay,
lecture.
so
Okay.
Yeah.
Thank you.
thanks. See you on Thursday.